All right, 9L, 9M. So we start off with refocusing on limits. So previously on first principles, I already introduced the idea of limits. Just as a reminder, it's a way to predict what the y value would end up being as I approach a certain value. So sometimes I don't know what the actual value is, but if I look at it and predict what it might tend towards, like asymptotes, that's what limits are for. So here's an example where it says evaluate the limit of f of x. Okay, so f of x is this hybrid function or piecewise function. And as I approach x equals 1. So x equals 1 is, actually that should be negative 1 there. That should be negative 1, fix that. So as I'm approaching negative 1, I can approach it from the left side and I can approach it from the right side of the function. If I'm approaching it from the left side, okay, so I'm coming from the left, so as x is negative infinity and I approach negative 1, so on the x-axis I'm going this way, right? Then on the graph, the y values is approaching as I get closer and closer to negative 1, the y values are also getting closer and closer to negative 1 from the left. Okay, so from the left, I'm approaching the y value of negative 1. Okay, even though it has an open circle there, it means it's not exactly a negative 1, but I'm approaching it. So it must mean that I'm getting close to negative 0.1111, okay, or negative 0.0001. I'm very close to negative 1. Then I'll look at the right-hand side. So I might say, all right, well, what does it approach when I come from the right? Now, when I come from the right-hand side, so on the x-axis from positive infinity all the way to negative 1, going that direction, then you can see that the y values are approaching as I get closer and closer to negative 1. There is a coordinate, an endpoint at 4.5, which is here. So what that means is approaching from the right, I will get, as I get closer to negative 1, we can see that y approaches 4.5. That discrepancy, where if I said at x equals negative 1, which one's the answer? Is it actually 4.5 or is it negative 1? Well, we know there's a dot, so we'd say it's 4.5. But in terms of the limits don't exist because the limits don't match from the left and right. So it depends on which direction I'm coming from. If I'm coming from the left, it's approaching negative 1. If I'm coming from the right, it's approaching 4.5. So there is no commonality in terms of the limits. So in this case, if I said limit of f of x, and this is the language we say, limit of f of x as x approaches negative 1, okay, we say it does not exist. And how do you prove that? You would say something like limit of x approach negative 1, f of x, and you put a little sign at the top. Say, is a negative for saying from the left, or you say a positive, which is a plus, to say whether it's coming from the right. So you would say something like from the right, this is approaching 4.5, and limit of x approaching negative 1 from the left is equal to negative 1. And these two, where they're both not equal to each other, that's when you can say, therefore, limit doesn't exist. Why am I teaching you this? Is because when you need to prove if it's not continuous or not differentiable, you need to go through those two steps to justify that limits do not exist. Okay, so you'd say something like limit from the left is approaching da-da-da, limit from the right is approaching da-da-da, they don't match, therefore limit does not exist. Yeah? So that's more of just a language and how do you justify yourself to prove? Because today's lesson is really focusing on these two words, continuity and differentiability. Okay? All right. You've got a note. Grab this one. Differentiability. All right. These are just some properties. So if you wanted to practice limits and you're not so familiar with it, generally I think special students already do limits, so maybe they're a bit more familiar with the properties there. These are some examples very similar to last lesson when I did, not last lesson, but when I did first principles. The aim is to make sure the denominator does not become undefined, then it becomes useless to us. I just realized there's also a mistake here. This one should be negative 1. And I'm not sure what that bottom one should be yet. 7, 2. 7, 2. Maybe it is -2. I think that A is meant to be a -2. I probably haven't finished it off yet. Yes, +7 -2. -2, then that means it should be +2. Approaching +2. Just fix those two if you wanted to have a go with the practicing limit. So there's parts of the exercise where it gets you back to first principles and seeing, can you reduce the fraction so that it becomes smaller, and then you apply the limit. Okay? But today's lesson, I'm focusing on continuity and differentiability. If you want some individual support, I can help you on the side with limits. But using the theory that I just said at the start here, we're now going to go into continuity and differentiability. So flip over the page. All right, let's have a look. So the two definitions that they will likely ask you in the exam at least once in your SACs is very common. A function f is continuous. So what does it mean by continuous? In a nutshell, the informal definition is the one I've given you here. Function is continuous if you can draw the entire graph without lifting your pen. That's the best way to remember it. But that's not how you should write it in your exam. So you shouldn't say, to justify that it's continuous, that you can draw the graph without lifting your pen. They won't accept that. Okay, so you actually have to go through these two key conditions. Okay, but just for your own understanding, any of these graphs that you can draw without lifting your pen, that's going to be continuous. First one is not continuous. Why? Because I can go straight. Yep, I'm keeping my pen, but then I have to let go because there's an open circle, dot, and then I continue again. That is not continuous, just based on the informal definition. If I went with the second one, B, again, it's not continuous because, again, I can go here and I have to let go of my pen, lift it up, let go of my pen, lift it up, and do it. So this is not continuous. And same thing, even with the third one, I'd have to lift my pen to continue drawing. So most times you can almost see it just by seeing any disjoint sections. That would be discontinuous. Well, which one's continuous then? If you look at the bottom, not this one, the next page, there's two here. Actually, all three is continuous. So I can draw this. That's continuous. This is continuous. This is continuous. Okay, so there's a difference between continuous and then differentiability. In this one, I'm going to prove to you where they're not differentiable, but that's for the next part. So as an informal definition, we were able to say these three, all three of them are discontinuous, but you've got to prove it. So how do we do it? We're going to use the limits again. So what are the conditions mathematically to prove that it is continuous? Well, the first thing is, and they're right in this way, it looks complicated, but it's not. All it's saying is that for it to be continuous at that particular point, right, x equals a, at that particular point, there should be a y value. So this is just saying, does it have a y value? So at x equals a, does it even exist? Does y even equal to anything? Okay, so can I sub in a number and get a number back? That's what it's saying. If you can, it's like, great, you've got a point. But just because you have a point doesn't mean it is continuous. As we saw in the first example, I do have a point. At x equals 1, I do have a y value, y equals 3. But that doesn't automatically mean it's continuous. So how do you prove it? Well, we can tell by not being, that we had to lift up our pen, or we can tell there's a discontinuity here, or disjoint part. But how do you show it mathematically? Well, clearly, if I start looking at the limits, if I'm approaching from the left, and then I'm approaching from the right, okay, I'll get a limit. The second condition is, does the limit equal to your first condition? So I'll say that again. So remember the first condition was, does a y value exist? It's like, yes it does. We had, when x equals 1, y was equal to 3. So yep, condition 1 was met. Condition 2 is saying, well, does the limit, as you're approaching that same value from left and right, does it actually equal that same value? Because if it doesn't equal the same value, it means at that particular point, they're approaching something totally different to the actual y value that you're getting when you're substituting. If they all match, if all condition 1 and condition 2 match, it is continuous. Okay, so there's two parts there. So 1, does the y value exist? 2, does the limit match that y value? That's all it's saying. So here, if I had to describe it, this just says, does limit match the y value? So first one was, is there a y value? Second one is, does the limit match that y value? Okay, and that's the proof for continuity. So here, if I had to prove it, let's do the first example, A. So if they asked us to state where, says state the values for x for which the functions shown have a discontinuity. We already know it's at x equals 1, so let's show that. So at x equals 1, so here we go. At x equals 1, condition 1 was to check if there's a y value. So f of 1, yes, it does. There's a y value at 3. So condition 1's good, no problems. Condition number 2. Condition number 2 says that if I check the limits from both left and right, does it exist? And if it does exist, does it match with that y value? Here we go. Limit of x approaches 1, okay, for f of x. What we can see is that it does exist because from the left to the right, they're both approaching 2. The y value is approaching 2. So I'm saying, okay, well, yes, the limit does exist, and as it approaches 1 from both left and right, it equals 2. Condition 2 says, does this number match with number 1? So in this case, you would then say, since limit of x approaches 1 for f of x does not equal to the f of value of x, which in this case, f of 1, I should just write here, which you have to show it. So you say it's 2, does not equal to 3, therefore not continuous at x equals 1. Does that make sense? So there's two parts that you got to prove. Okay, 2 parts that you got to prove. You got find the y value at that point. So at x equals 1, clearly the y value is 3. So yes, we've got a point. Number 2 is find the limit as I'm approaching it from left and right. What is it equal to? If it doesn't match already, you just say limit doesn't exist, therefore condition 2 is not met. Okay, but if there is a limit, then you're going to check if the limit equals to either each other. Okay, let's try next one. B. Where would it be discontinuous? So now we're trying to find points where it's discontinuous, because that's what it's asking. It says state the values of x for which it is going to be discontinuous. Where can you see in part B that's going to be discontinuous? Can I please have, let's go with Krish. Very good. -1 and 1. We can see that's where we're going to lift our pen off, right? So at x equals -1 and x equals 1, those are the 2 points you have to prove. So here, if I had to prove at x equals to -1, at x equals -1, testing the 2 conditions, condition 1, is there a y value? So does f of -1 even exist? Yes, it does. It's got a dot there, and that exists at roughly 2, approximately. Okay, but it exists. Condition number 2, okay, so yes, there's a point, but what's the limit? So here we go. If I approach from the left, this is where the graph is approaching, and it's approaching 2, right? So limit, approaching 2 from the left. But if I'm approaching from the right, if I'm going towards x equals -1 from the right, what you can see is the graph goes to -infinity. So here, this is an example where the limits don't match. They don't exist. So here you have to say something like limit of x approaching -1 from the left for f of x is equal to 2. Limit of x approaching -1 from the positive side for f of x is equal to -infinity. Limit of x approaching -1 for f of x does not exist. Okay? And since this doesn't exist, then therefore condition number 2 is not met. If condition number 2 is not even met, if there's no limit, then you can't even match the limit with condition number 1. So hence, discontinuous. Okay, so unlike the first one, yes, the limit did exist. It actually equals to 2. And then you have to match, does the limit match with the y value? No, therefore not continuous. Second one, yes, we had the first condition, but the second one, the limits do not match from left and right. Okay? Let's try C. Oh, sorry, I forgot. We still had to do number 1 as well. So if we did part 1, so at x equals to 1, y is a discontinuous again. Is there a y value? Condition 1 is met. So f of 1 does exist. It's equal to 2 as well. Then condition number 2, does the limit exist? So here we go. We go from the left. You can see that the left would approach. As I get closer to 1, limit from the left is 2. So limit x approaching 1 from the left is equal to 2. And limit of x approaching 1 from the right, we're approaching 3. So again, limit of x approaching 1 for f of x does not exist. Whoops, doesn't exist. Okay. I mean, you could write that in one go. You could write limit of f of x from -1 and then do that cross equals. So not equal to sign, limit of a right, and you can just write 2, 3. And that's in one sentence as well. And then you say, therefore, limit doesn't exist. Okay, that works too. Part C, hopefully you picked up the idea. Where is it discontinuous for part C? Let's go with Aryan. So if you're looking at part C, where is it discontinuous? 1. Okay, we can tell it's at x equals 1. So let's test you guys now. So remember the 2 conditions. What's the first condition, Zach? To prove that it's discontinuous?
If it's real, if the function has a single x value, y value and an x value.
Very good. So at x equals 1, you're just testing, does f of 1 exist? In this case, does it exist?
Yes.
Where?
At 1.
Very good. So at 1, 1. Okay, so therefore, yes, it does at 1, 1. So condition 1's met. What's condition 2 again? Can I please have Anne? What's condition 2? So yes, there is a y value. What's the second thing you have to test? Very good. So you have to see if limit exists, and if it does exist, does it match with the y? So here we go. Limit from the left. Limit from the left, Samar, what is it approaching? 1. Very good. So limit of x approaching 1. Whoops. I'll do 1. From the left for f of x. Does it match with the right? So the right side we can see it's approaching 2. So I would say limit of x approaching 1 from the right does not match. And we can see that 1 is 1. Does not equal to 2. Therefore, limit does not exist. Okay? Doesn't exist. So far, so good. So that's the first part of, I think it was 9L. That's continuity. So you're just practicing to justify that. But what I just did there, that's pretty much all you need to do. Why do you need to know continuity? Because differentiability requires that it has to be continuous first before you can even test for anything else. So I'll leave that example here for you to practice just justifying. But if you flip over the page now. So today I was trying to teach you 2 key things. I was trying to teach you continuity and then differentiability. Differentiability just means, does it have a derivative? So you did all these rules, you're learning all these rules just to find a derivative, right? But then at certain points, it won't have a derivative, meaning there's no gradient for a tangent line. So all 3 of these are continuous. We've already proven that point before. All 3 of them are continuous, and you can prove that by going through the 2 conditions. Then what's differentiability? See, differentiability has 2 conditions as well. First one requires that it needs to be continuous. Okay, so every point has to be continuous. And at that particular point you're looking at, it has to be continuous. Then the second part, which is very similar to the first one, you're checking if the limit of not the y value this time, but the limit of the gradient, does it exist? Okay, so you're looking at the derivative. So this is the only part that just adds another layer to it. So let's have a look at the first example. We can already tell it's continuous. And if you had to prove it, we'd have to go through the same conditions we just did. So here, the only part that might be skeptical is that x equals 0. Okay? And that's what I was trying to say in the last video, where I was saying any sharp points or any end points. So this one has a sharp point up here. Those points will have a problem with differentiability. And here we're going to prove it. So this sharp point, we're going to prove that it's continuous, right? So to be continuous, does f of x equal to 0 exist? Yes, it does. So continuity, first part of the condition is true. Part 2 is to check if the limits exist. So here we go, limits from the left. So limit of x approaching 0 from the left equals, in this case, 2. And if I approach from the right, it's also equal to 2. So they're both equal to 2. Great. But remember, condition 2 was to see, does this match with the first one? Yes, they do. Therefore, limit of x approaching 0 for f of x does equal to f of 0, which is equal to 2. Hence, continuous. Great. But the second part, to check if it's differentiable, so here we go, now I'll do it another color. So we got it's continuous. Number two is to check the limit of the derivative. So the gradients at that particular point. So limit of x approaching 0, does the derivative exist? Now here we go. If I asked you to find the gradient from the left side, so the gradients at each point, what's the gradient at each of these points at the moment? Let's go with Charlie. 0. Each of them. It's a nice horizontal line. So gradient 0. So this has a gradient of 0, 0, 0, 0, 0. So by the time I'm getting to x equals 0, I would expect that the derivative is approaching 0. Right? But then if I go from the right, so limit of x approaching 0 from the left, for the derivative, it's approaching 0. Versus the limit of x approaching 0 from the right, if I'm coming from the right, we can see that the gradient in each of these points, and I may not know what the gradient is. I know it starts at 2. I don't know what the gradient is, but I can tell you one thing, it's positive. It's not 0. It's positive there, positive there, positive there, positive there, and it's consistently positive as well. So therefore, whatever that value is, the derivative is going to be greater than 0. You can do it like this. These two won't match. From the left and from the right, they're not going to equal to each other. Because they don't equal, limit of x approaching 0 for the derivative does not exist. And because the limit doesn't exist, that means going back to this very top bit, we got the first bit. Yes, it worked. Didn't work for the second bit. Therefore, it's not differentiable at x equals 0. That's why anything that's sharp, because sharp, especially if it's linear, sharp would imply that the gradients suddenly change dramatically from the left and right. So one would be like negative and the other one suddenly is positive, or one's 0, one's negative. So because of that, any sharp points will indicate that. So you can see over here, we can sort of see the derivatives. Each one, this is growing in positive. It's going towards positive infinity, right? Whilst this one, the other way, it's negative. All of them is negative. So you're going right up positive infinity versus one that's going down, that's negative infinity. Yeah, so it's like infinitely that way versus infinitely this way. They're both not going to match. So you can already say that at x equals 0, limit of the derivative does not exist. And that's how you prove that it's not differentiable. Yeah, continuity you already saw. You can just prove the continuity by either looking at it, but if you're in a SAC or an exam, you got to go through all those 2 steps to prove it. Okay? And then lastly, if you look at the middle example, this one's an example where all of it is differentiable at all points. and it is all continuous. That's why when you find the derivative of a linear line, you just get the gradient, which is 0. Okay, so it's differentiable at all points. So at the final part, that's the skill for L and M, is to be able to do what I was just doing, justifying each step to prove whether it's continuous or differentiable. In terms of your own general knowledge, the only times you don't have derivatives is when it's sharp points, any sharp points, and endpoints. Okay? So those are the two key things for non-differentiability. If you were to quickly decipher it, find sharp points and find endpoints. That's where it is for you to do the test. Okay? But that's it for today. You guys can try any of these if you want, or the exercises. They essentially just get you through the pretty much, if I had to break it all up, it's 4 steps. Each one. To prove it's continuous takes 2 steps. To prove it's differentiable takes 2 steps. Yeah, so 4 steps in total. That's L and M. Theoretically, it's a very small component in your exam, in your SAC. I would say your first thing in Chapter 9 should be learning all your skills. You should all know how to do chain rule, product rule, quotient rule, all by hand and by calculator. You should also know all your general rules like sine, cos, tan, exponential, log. That's the main thing to take away. Okay, so I don't mind if you're a bit behind, just make sure those skills should be ticked off. First principle is really small. Don't really need to know it. I believe it's in the year 11 course, but not year 12. But the theory behind it is still needed. Okay? All right, we'll stop the video there.